Hello and welcome everybody. This is again the MATLAB and Simulink Racing Lounge. In today's episode, we are going to talk how you can model your physical system of your race car. For that episode, I'm really glad to have again a guest presenter on board. So welcome Sebastian, welcome to the Racing Lounge.
Hey, thank you, Christoph.
Sebastian, could you introduce yourself briefly? I think guys want to know what your background is and why you're the right guy for that episode.
Sure. So my name is Sebastian Castro, and I'm with the training services team here at MathWorks. Mm-hmm. I'm a content developer for modeling and simulation courses with Simulink, and my background is in controls and mechanical engineering. Mm-hmm. So, yep.
Cool. So maybe some of you who have already attended a training, it might have been developed by Sebastian. So that's good. I think I will guide you briefly through today's agenda, and then I will hand it over as usual to the guest presenter. So what we are going to do is we introduce you to modeling in general. We will see that models can be quite different. So some can be based on equations, some can be based on data. Sometimes models can be comprised of both. We will introduce you to that, and we will always combine it with a software demo. So whenever we show you a modeling approach, we will combine it with a software demo so that you get most out of it. And last but not least, and the frequent viewers of the Racing Lounge know that we are quite critical to ourselves and present the key takeaways. So Sebastian, at that point, I'm handing it over to you. The stage is yours.
All right. So thanks for the introduction. Let's talk first, as the agenda says, as to what is modeling. Mm-hmm. I want to talk to you about the different types of modeling that you can do using simulation tools like Simulink. Generally, when we think of making a model, we can divide it into two parts. The first one, which is the one we're going to talk about for today's session, is this notion of a plant model. What this means, it's a controls term, mm-hmm. is that this is going to be a virtual prototype of a real physical system that you're trying to model. For example, if you're trying to do some kind of simulation of a car, instead of testing things on the car itself, you can take advantage of simulation, so it's a lot easier for you to try out different things without having to go to the shop and build things. And what we'll see throughout the session is that there's many different ways that you can model these systems, whether it be taking the mathematical equations from physics or collecting data and doing something with that data that you get. Mm-hmm. So in summary, the plant is going to be just a simulation of the real system that you're working with. The other part of the model is kind of the reason why you're going to be doing anything with the car, for example, is that of your algorithm. So your ultimate goal, for instance, might be that you want to have good control of a car or control of an engine. So instead of testing your algorithms, your control, your logic, etc., instead of testing them on the real car, you can test them on your simulation. So what usually happens is for the algorithm, you're going to be doing your testing on your computer and then maybe taking that to an embedded system with code generation or simply by translating it by hand. So those are the two types. Now, one of the cool things about using Simulink is that you can combine these two, and for both of them, you have several analysis tools that you can use to improve your designs. What we mean by that is, for example, on the plant side, you need to make sure that your plant model is as accurate as possible a representation of the real system. Or for the algorithm, you want to make sure that that control or that logic system has the best performance possible. So there's a lot of analysis tools that you might have seen in previous episodes.
Okay. Yeah, actually right, Sebastian. This is the PID tuner that we have just seen in the previous episode of the Racing Lounge that I've done together with Daniel, and we've been talking about the basics of control design.
Exactly.
I think you already mentioned it, but for us mechanical engineers, I think that might be a really valuable information. When control designers or control engineers talk about plants, they actually mean physical systems, right?
Exactly, yep.
Okay.
So, again, the plants could be a car, it could be an engine, mm-hmm. or it could be something that we'll look at for this session, mm-hmm. Which is going to be a suspension model.
Okay.
Before we get into that, let's talk about the different types of modeling for physical systems, because there's mm-hmm. quite a few different ways you can do this. There's generally a spectrum there that goes all the way from equations on the left mm-hmm. to using data on the right. And we'll use a few examples of that to explain what these mean. On the equation side, what we usually mean here is mathematical modelings, or models, which use first principles. Mm-hmm. First principles means that you take equations of physics that are well known, like force equals mass times acceleration, for example, mm-hmm. and you build the math for your system. So that's one way. Another one is to use component-based physical models, where you might know, for example, that your system is made of springs and dampers, and you know what those equations are, so you just connect them together.
Yeah. But let me ask a question at that point. So to do it the mathematical way, you really have to have a good understanding of your model. You really need to be able to derive or write down the equations of the system, right?
Right, yeah. You're going to have to be able to write all those down, mm-hmm. and then once you have the math in front of you, you can translate it into your simulation tool.
Mm-hmm. Got it.
So while it's a very well-established process to have equations, you will have to do the derivation and translation yourself.
Exactly. Sure. Well, that leads me directly to a question. What if I don't have access to the equations? Just assuming that my system is too complex to be modeled right away, or if I don't have enough data, what can I do?
Right. So one thing you can do is to collect data. So let's say you have an engine in your workshop. Mm-hmm. Maybe you know that there's some kind of inputs that you can provide to that engine, mm-hmm. and you also have some measurement devices, let's say, that you can use to collect those outputs. So now you have a relationship between the inputs to the system and the outputs. Mm-hmm. But you don't know what's happening inside, so you don't know the equations.
Yeah, but I think this is a pretty realistic scenario. So you have, for example, as you say, an engine on a test bench. You give certain throttle commands to the engine, and you definitely can measure the RPM or torque output.
Yep, that's exactly right. So as you see on the right there, the black box models kind of fit this situation that we're talking about. There are a few things you can do. If it's a pretty simple component, you can create a lookup table. Okay. And what a lookup table is, you basically have just a very simple relationship between the inputs and the outputs. Yeah. But if you need a more complicated one that has some, something dynamic happening inside of your system that you don't know, then there's other techniques like system identification, where you don't know anything about the equations, but we can use tools that can fit equations to your data. Okay. And while it doesn't require you to know math, or at least in the same sense as the mathematical models, there is a lot of art in getting those approaches to work, as we'll see.
And as there is quite some space in the middle of the slide, I assume that there are some intermediate techniques. Is that right?
Yeah, so there is a combination of those two. Mm-hmm. Take, for example, that you know all the equations of your system, but you're not quite sure about the numbers. Okay. And this is what we typically refer to as a gray box model. Mm-hmm. One of those examples is parameter estimation, where, again, you know a good amount about the system, but there might be certain things that you're not quite sure about. So what you can do is you can write down some equations, as well as collect data, and then use that data to tweak your numbers and modify your equations so that they match your data.
Okay. Well, that makes perfect sense to me. I think now it's time to introduce our viewers to the model that we want to use during the session, and start with the first modeling approach.
Absolutely. So as I mentioned a little earlier, we're going to look at a suspension system. It's a system that we chose because it's very easy to wrap your head around the equations that could describe the system. But also, we can abstract this to only have input-output data. So let's talk about the system a little bit. As you see here, we've defined an input, which is the road position. We can also treat this, whether it be the position or the road velocity. We could use either of them here. So you have a road that might be bumpy and it's moving up and down. Yep. And then you have some springs and dampers. You have a mass that represents the wheel or the suspension system of your car. You have more springs and dampers. And then finally, you have a bigger mass at the top of the assembly, which is going to be the car where the driver is sitting.
No, I think most members of the former student community will agree on that, because between a car and the wheel, you actually have a spring and a damper in most of the vehicles. And also, it's a pretty common assumption to model a wheel or the wheel-road interface also using springs and dampers. I think that's a quite good example that you've picked for that episode.
That's good. Yeah. indeed, people do use a spring and a damper to represent the wheel-road interaction as they model the wheel kind of squishing against the road.
Yep.
So what we're interested in is going to be the position of the car. Basically, we want to see how good is our suspension system as we move the road up and down.
Yep.
As we're moving along it, then how does the driver feel that motion? And that's kind of what we want to know in this example.
Okay.
So we'll start with the one we're most familiar with, which is going to be mathematical modeling.
Okay.
So you get your pen and paper out, you write down your equations, and you get something like this.
Okay, so we've done it for you, no worries. If you want to pause now and have a look at the equations, feel free. We hope they are right. And based on these equations, what is happening now? How can I get a model from that, Sebastian?
Right, so first of all, there's plenty of ways to get a model.
Yeah.
The first thing that you want to consider is the dynamics of the system. So one thing you'll find is that, for example, here we have the position of the car, which is x car. But our equations, the way that they're lined up, we also need to know the first derivative of the car position. That's going to be the speed of the car. And also we need to know the acceleration. So that's going to be the second derivative of the position.
Well, just a comment here. When talking about the speed of the car, we talk about vertical speed. So just to be clear on that.
Exactly. Yep. So we're doing that vertical model of the suspension. So the way that I like to look at it is then you start with the highest order term, so that's going to be the acceleration. And then you know that to go from acceleration to speed, you have to do some kind of integration.
Exactly. Yep.
And similarly, to go again from this vertical speed of the car to the vertical position, you have another integration going on. And there's a magical Simulink block that takes care of most of this for you, which is the integrator block.
Okay.
And that you can combine this with, all your other mathematical blocks to build a model like I just showed here on the slide, where you'll notice that you have integrators here for the car, the wheel, and the road positions.
Okay. Sebastian, let me ask a question at that point. So, well, the model that we see here looks quite structured. So wheel at the bottom, car on top. But it also looks quite complex at first sight. So can you comment a bit on the strategy, how you put it from the equations to the actual model?
Yeah, so first of all, it's kind of an art to get these lines to look as good as possible. But even though I've tried, you see that there's a lot of line crossing.
Yeah.
And that's something that when you're making a Simulink model, and depending on how complex it is, it's something that you kind of have to live with.
Yeah.
The reason for that is that if you look at the way the equations are structured, is that they always start with, again, our good friend Newton, which is tells us that the force is the mass times acceleration.
Exactly, yeah.
Where mass times acceleration is this first term right here.
Yeah.
So we're saying then that this term is equal to a combination of everything else that's on the right side. So we can kind of refactor that equation.
Okay.
And as you see here, basically, we can map the acceleration of the car, for example, to this point right there. And then we have a double integrator, which gives us then the position and the speed. But you have to use the position and the speed to compute forces for the next time step. So that creates that kind of cycle behavior where you always have to constantly create loops in your mathematical model. So that's why it looks the way it does, and it's something where, again, it's a machine that's constantly running and giving you the mathematical results.
Well, just a question to you, viewers out there. If you want to have an episode about, well, focusing more on how you come from equations to a Simulink model, for example, just let us know. I think it would be straightforward to prepare something on that. But I think, Sebastian, thank you very much for that introduction. I think we all trust you that this model is correct. Can we have a look at that and see how the car actually behaves?
Absolutely. So let's get out of PowerPoint and let's go to MATLAB. Okay. So I'm going to open up one of the models that I have prepared for you here, which is the suspension Simulink. And I'll just load this up and have it fit on my screen really quickly. So you have all your blocks. What I've provided here is I have an input, which is right now just a sine wave.
Yeah.
This is going to be the velocity of the road that we then convert from centimeters per second to meters per second. just because we like to use SI units as much as possible.
Mm-hmm.
And after going through the model, we take some of the outputs on the right side, and we have a scope here that gives us the position of the road versus the position of the car.
Okay.
Both of them in centimeters.
Yep.
So I'll just run that and load up my scope. What's happening here, you see that the road is oscillating quite a bit, and it's going between about, let's say, plus and minus 2.5 centimeters. So that's how this road is moving.
Yeah, quite bumpy, but why not?
Yep. Why not? And then you see that initially, when the car first engages that bump, it also has some pretty large oscillations of its own, but they're not quite as large as the road position because of the suspension system.
Yep.
So you see the car position, it has a maximum of about, I guess, 0.15 centimeters and a minimum of about 0.1 or negative 0.1. And because of the damping in the system, it slowly dies down.
Okay.
Back to a stable position. So you'll see that this suspension is doing an okay job. Even though our road is moving about 2.5 centimeters, the driver never sees even a single centimeter of motion. Though there is a little bit, of course.
I think we can compare that situation by a car just driving on a very smooth, perfect road, and then all of a sudden coming on a gravel road, which causes the suspension somehow to excite. Well, that creates some movements in the car, although they are very low. And after, let's say, 4, 6, or 8 seconds, this is reducing, and the car is getting in a more harmonic, a more smooth mode of driving.
Right. So one thing we could do is always take some of these parameters and change them if we wanted to explore the effects. For example, I could take the damper here, and I could increase its value if I thought that was something we wanted to try. Where I can say, for example, B1 is equal to B1 times 10. So I'm just making it 10 times the value that it was before. And if I do that, maybe the value is not going to be realistic, but that's the beauty of simulation. You can just change things and see how they behave. And as I'm just going to scale everything, you see that maybe we have to change other parameters there. But we at least remove the high-level oscillations a lot quicker.
Okay.
Again,
So
there might be other things we can change. All right. Now, for those who are used to making these dynamic models, if your model is nice and linear and well-behaved, instead of using the Simulink model here, we could always take all these equations and put them in other forms that may be familiar to us, like transfer functions, for instance, or state space models. As you can see here, for example, because this model is fully linear, we could collapse all of this here into a single block that contains the equations in 4 matrices, A, B, C, and D. And I'll bring up that model just to show you what's going on there too.
So basically, that sounds a bit like magic to me. But can you comment a bit on the way of obtaining that state space matrix?
Yeah. So unfortunately, I'm not doing anything too magical. It's only going to be a different way of modeling the same equations. So in other words, it is still my job as the person doing the modeling to come up with those matrices.
Okay. Well, at the end, it's writing the equation in a structured form. So always have the accelerations in one column, having the velocities in one column, and then putting the parameters to a matrix.
So, well, what I have, for example, is I've set up this model preload function to create the matrices for me when I open the model. And here you see that I've used the same parameters that we spoke about before, like the springs, the masses, the dampers, and I've just formatted them in this state space form so that I can then use these matrices in my model. And you see, for example, over here I have my 100s, which are my unit conversions from centimeters to meters. So I can run this model. As long as I'm using the same inputs, I should observe the same outputs as well.
Okay. Okay. So, well, this can be greatly simplifying the work. So not any time it's really required to set up a Simulink model when you can model it with a lot less blocks.
Right. If you're comfortable with the state space approach, that is.
Yeah.
But yeah, there's many more blocks that you can use to model these physical systems. All of them, you can find them in the Simulink library under continuous. You'll find quite a few different blocks like integrators with limits, transfer functions, and all that. You can find it there. So.
Okay.
Great.
Well, I think now it's the time to move to the second real modeling approach. You said you can actually model the physical system directly. So I'm really curious about seeing that.
Yep. So let's remove the focus from equations a little bit, and let's talk about the next part, which is component-based modeling. So maybe let's talk about what it is first.
Yep.
Here is an example of a component-based model, and it's developed using one of the Simulink add-on tools called Simscape.
Okay.
Have you guys spoken about this in the Racing Lounge?
Yeah, we have had an episode where we've talked about suspension modeling. Therefore, I've used sim mechanics, but I feel I haven't properly introduced our viewers to that. I've just used it and said, well, that's it. It made sense. But it's very good that you mentioned the basics behind that. So Simscape is, well, what we call it, a tool for physical modeling, or in that case, we said component-based modeling, well, which basically uses blocks that have the equations behind. So I think
exactly.
Okay, but you're the professional here, so perhaps you can guide us better through the way how you can model it using Simscape.
Okay, so let me just go back to MATLAB then. I have another model which models the same exact thing called suspension Simscape. Let's just get that loaded.
Yep.
Again, as Christoph was saying, is that at this point you don't really need to know much about the equations. You can instead assume that your model is made of separate components. And for a model like this, it's a nice one to talk about because we saw that we could make our model entirely out of masses, springs, and dampers. And just by connecting them to each other, you're making sure that the energy can flow in both directions from one block to the next, which means that you don't have to create these crazy feedback loops like we did in the first case.
Well, and I also see that if you add some complexity to your model, it doesn't require to do the model completely new. You just can copy and paste some blocks.
Exactly. So let me bring up the scope of the results here, just to show you what could happen if I wanted to add something on top of the car for some reason. Then instead of having to go to my pen and paper and rederive the equations, I could just take these blocks. I could copy and paste, and I could simply, stack more things on top of each other. And Simscape is just going to take care of all these equations for me and lead to different results, as you see there.
Okay.
So it's very nice, especially if you're exploring different configurations of things. You can imagine one of the examples might be, for instance, do you want suspension on your front wheels only or on your front and back wheels? I don't know. That's maybe not the best example, but it's things you can try. You can try different configurations very easily by dragging components around.
Well, I think something that we should mention here is Simscape and Simulink are compatible. So it's perfectly possible to have a control system, usually done in Simulink, and plug a plant model in, which can be a Simscape model.
Exactly. You see that there's kind of interface blocks between Simscape and Simulink. These are the Simulink to physical signal and physical signal to Simulink converters.
Exactly.
And another cool thing they do is that if you're working with different units, for example, you can always click these blocks and configure the right units. Notice that I don't have any 100s in this model. I've simply specified units of centimeters, and the tool is smart enough to convert them for me.
Great.
So I like that quite a bit.
No, that's cool. I think now we should move over to the point, well, what if I don't have access to the equations? And what if I don't have enough understanding really to set up my model from scratch?
Yes, let's talk about data. Equations are fun, but again, we don't always have them.
Exactly. Yep.
So I'll first start by looking at an extension of the model we already talked about. That's going to be through the use of lookup tables.
Yep.
Suppose you now have a nonlinear spring. Maybe you have either a data sheet or you've conducted an experiment yourself where you've taken measurements of the displacement of a spring versus the force that it provides.
Okay.
And you get a graph like you see there.
Well, this is a completely realistic example because I know that quite some Formula Student teams use air dampers, which experience a nonlinear behavior compared to a spring made from metal. So I think this is a pretty realistic use case you're showing here.
Yeah, that's good to hear. So yeah, it's great because in this case you don't have to create equations for your system. By collecting such data, for example, you can have a simulation that, let's say your displacement is 1 centimeter, then you can simply, draw a line. Oops, where did my line go? You can draw a line upwards here and then trace it to the location over there, and then say, oh, if my displacement is 1 centimeter, I should expect a force of maybe 800 newtons or so. So it's a good way of introducing small components that have a very simple input-output relationship.
Yep.
And you can do that with many different ways, like using Simulink lookup tables, or even using Simscape blocks, like the nonlinear spring there.
Okay, well, this is very interesting. Let me ask a question at that point, because is it possible to import, for example, data from Excel sheets or from text sheets to that blocks?
Absolutely.
Okay.
And that's one of the great things about having a platform that sits on top of MATLAB, right? Maybe you've seen before that with MATLAB you can do lots of different file imports.
Yep.
For example, reading from Excel files or from text files. So I don't have an Excel file here, but I do have a mat file that contains some of the data that I've collected. So I'm going to, first of all, clear my workspace, and then I'm going to drag this file. And you see here I have a couple of variables. So as long as you can read your file and get similar numbers into MATLAB, from that point on, then you can enter things you want into a lookup table.
Exactly. And this is a topic there where we had an episode of the Racing Lounge importing data to MATLAB. Yep.
Ah, great. So before I go into Simulink, I just want to plot the data in MATLAB to show you what's going on here. As you see there, you have your displacement in centimeters at the bottom and then your force at the top.
Yep.
So we want to take this data and put it in a Simulink model. I'm going to show that to you using the Simscape model right here, where you see that I've replaced one of the spring blocks with this nonlinear translational spring. And when I look in here, you find that I have a parameterization by lookup table where I've entered my deformation vector referencing that MATLAB variable x that we had there in centimeters, and then also my force vector, which is fs, also in our workspace.
Okay, just the MATLAB variables. Okay, that's cool.
Yep.
That's pretty.
So you can enter all sorts of MATLAB variables. And with this relationship, you would see slightly different results in your simulation, as you see there.
Yep.
Not too different in this case, but it could be.
Yeah, and this is a pretty realistic use case. Good to have that. Yep.
But the problem arises that this is only good for very small components that have a very simple input-output relationship. Once you start dealing with dynamics, it's harder to deal with the numbers.
Yep.
So we'll see some more approaches involving data at this point.
So we are moving to the right of the bar you've shown at the very beginning, away from clear, strict mathematical modeling up to the black box modeling.
Exactly. So we've seen the lookup tables.
Yep.
So at that point, let me do a recap of what we've covered so far in part 1 of the current episode, modeling physical components. We've talked about mathematical modeling. Sebastian has introduced us to component-based modeling using Simscape, and we have introduced the concept of lookup tables. In the second video, means in part 2 of the current episode, we will talk about parameter estimation, we will talk about system identification, and we will see a summary of the entire episode. So looking forward to seeing you again. Part 2 will air on June 10th. Looking forward to see you there. Stay tuned.